All right, so let's jump right in. We're going to unpack a really fascinating scientific paper today, one that tackles a huge question by starting with, well, a bit of poetry. It's all about how we can understand massive, complex things just by looking at one tiny, tiny piece.
You know, the author of this paper was so taken with this quote from Khalil Gibran that they actually put it in the acknowledgement section. And it's a beautiful thought, isn't it? The idea that the entire secret of a vast, churning ocean could be hidden inside a single, simple drop of dew.
Okay, but that beautiful idea, it runs into a pretty big scientific problem, right? I mean, if you've got this tiny sample, a speck of dust from a comet, let's say, or one drop of water, how can you be sure it actually represents the whole thing? How do you know your dewdrop isn't just a little bit weird?
To answer that, we have to go beyond the most obvious place to start, just finding the simple average of what something is made of.
Think about it. When scientists get a new sample, the first thing they typically do is figure out its average composition, what chemists call the first moment. It's basically just a list of ingredients. But here's the thing. A list of ingredients doesn't tell you the recipe. It gives you no idea how those ingredients are actually put together.
And this is where the fruitcake analogy from the paper comes in, and it's just perfect. Imagine two fruitcakes made with the exact same average ingredients. One is beautifully mixed, right? Any slice you take is going to taste pretty much the same. The average works. But in the other one, all the fruit is in one giant clump. So a slice from one side is just plain cake, and a slice from the other is all fruit. The average is the same for both cakes, but it's totally misleading for the clumpy one.
And this clumpiness actually has a scientific name. Heterogeneity. It's the measure of how unevenly mixed something is. So if we really want to understand the whole from a tiny part, we can't just know the average ingredients. We absolutely have to measure its heterogeneity.
Okay, so if this heterogeneity, this clumpiness, is the secret sauce, how in the world do you measure it? Well, it turns out scientists have developed this incredibly clever toolkit to turn mixed upness into cold, hard data.
Yeah, I mean, really, how do you do that? How do you quantify something that sounds as abstract as the clumpiness of a rock, or a comet, or even that fruitcake?
Well, the method is actually pretty ingenious and way more intuitive than its fancy name radial covariance might sound. Let's just call it the proximity test. Here's what you do. You pick two random points in your sample, you check what they're made of. Then you measure the distance between them, and you just do that again and again, thousands and thousands of times. Eventually, you've got this massive pile of data you can search through for patterns.
And when you do this and plot all that data, what you get is amazing. A pattern emerges. It's not just a list of what's inside, it's a map of how everything is arranged. It's the material's unique compositional fingerprint.
So what is this fingerprint actually telling you? Well, it answers some really key questions, like are points that are close to each other generally similar? That would suggest big clumps. Or how far apart do 2 points have to be before their composition has absolutely nothing to do with each other? It lets you see if you're dealing with a random, well-mixed material or if there are ordered, hidden structures inside.
And here's what's so powerful. Even when the data doesn't fit a neat, random pattern, that's where the real story is. For example, if you find an area rich in one element that is consistently surrounded by an area that's lacking it, that's a huge clue. It hints at a history, a process of how things moved around, which is a story a simple average would miss entirely.
Now, this isn't just some abstract math problem. Not at all. This toolkit has some seriously mind-blowing applications for understanding our world, from the absolutely cosmic to the totally microscopic. Let's start with a really cool one, right from the paper's appendix, analyzing tiny specks of dust that have traveled between the planets.
So get this. Scientists are looking at these tiny, tiny grains, sometimes just nanometers across, that they collect high up in the atmosphere. By measuring the heterogeneity inside just one of those little specks, they can start to model the structure of the entire thing it came from, a comet that could be kilometers wide. It tells them if they should expect a clumpy fruitcake comet or a well-mixed one. This gives them way more confidence in their conclusions, which was absolutely vital for missions like Stardust that actually brought comet samples back to Earth.
Okay, but here's where it gets even cooler. You can take the exact same mathematical toolkit and apply it to something that seems totally unrelated. Instead of looking at the mix of stuff inside a material, you can use it to analyze the little bumps and valleys on top of it. In other words, to measure its roughness.
For instance, think about a grassy field. It has features, blades of grass, that are way taller than they are wide, so its roughness spectrum would show a huge spike at that specific scale. Now compare that to a silicon wafer for a computer chip, which is one of the flattest things humans can make.
its spectrum would be, well, almost totally flat. The exact same math can precisely describe both of these incredibly different surfaces.
All right, so let's tie this all together and go back to where we started, with that single dewdrop and the entire sea.
It turns out that Gibran's poetic line, well, it's not just poetry. It's actually a profound statistical reality. The secret isn't just about knowing what's in the dewdrop.
The real secret, it's in the structure of that tiny drop. The pattern of its variation, its internal clumpiness, the relationship between all its parts, that is the fingerprint of the massive system it came from. By analyzing that pattern, we can actually truly begin to infer the nature of the sea.
And you know, this idea is absolutely fundamental. It's how a geologist can understand a whole mountain range from a single rock, or how an astronomer can understand a distant star from just its light. We are always trying to discover the secret of the sea by meditating upon the dewdrop.
It just makes you look at the world a little differently, doesn't it? As our tools for analyzing these tiny parts get better and better, you have to wonder, what other huge, complex systems are we about to understand? What secrets are just sitting there, waiting to be found, not in the ingredients themselves, but in the hidden patterns all around us?